Right. So hello everyone. Welcome to the ECR seminar. Today we have our own Rodrigo Calderon. He did his PhD in Montpellier with David philosophy, and he's now a postdoc in CosKASI working in Harman. And today he's going to talk about phenomenology of some dark energy models. Please go ahead.
Okay, thank you, William. So, yeah, I was asked today to present my research interested, and I thought about basically do an overview of my past works in these last couple of years. So I will try to briefly connect different works and give motivations on why I was interested in such topics. And so we have previously a talk on observational supernovae cosmology. I will be a bit slightly more theoretical, but it connects very well with what Alex said before. So I think I don't need to introduce what the standard cosmological model is, what we call the concordance model, but let me just remind you that this model is a phenomenological model, which is based on various assumptions, namely that the universe is homogeneous and isotropic at large scales, that it is flat, and the dark energy is described by a cosmological constant that we call lambda, and that there is non-relativistic or cold dark matter, which makes up for 25% of the energy budget. And in addition to this, we have the assumption that the primordial seeds were basically set by an epoch of accelerated expansion that we call inflation, and this gives rise to an adiabatic and nearly scale invariant power spectrum. And so, as we all know, this model is in remarkable success with a wide variety of observations. So from supernova, BAO, we can constrain the equation of state of this dark energy fluid. And it points back to this -1, which corresponds to a cosmological constant. So the measurements of large-scale structure of P of K are also in quite good agreement with the standard model predictions. We have the CMB, which it's one of the main pillars of the Lambda Cdm paradigm. And we have BAO and other probes. And despite this model being in agreement, there has been a bit of a problem arising in the last 10 years, I would say. Namely in the value of the Hubble constant, which is, of course, the hot topic nowadays in the literature. But there is also some other inconsistencies, like the amplitude of matter fluctuations as measured by weak Lansing surveys on the right, which I show. So the late universe seems to prefer less matter. So the clumpiness of matter is lower than what we predict from the standard model of cosmology using CMB measurements. And there are other small-scale issues like some satellite or core cost problems that might point to some different nature of dark matter. Or we have the A-lens anomaly in CMB, we have the age of the universe problem, and many other problems that are less statistically significant, but they're still there. And so, why do we need to go beyond this Lambda Cdm model that works pretty well? So namely, as I said, because of these problems, they might be pointing towards new physics. But I think that even if these problems did not exist, as I said before, this is just a phenomenological model, and we have a lot of questions that are not answered by this model. And we can actually try to test the assumptions of this model. For instance, we can go beyond the FRW metric, and we can explore, for instance, in homogeneous or anisotropic cosmologies, as the one that I'm showing here. We could also explore many of the beyond standard model scenarios that particle physics models predict. So let's say we could have axion-like particles, which is one of the main solutions to the CP problems, the strong CP problem. And this could explain, for instance, the nature of dark matter. We could have the neutrino sector, which is very ill understood by particle physics models. So we could have self-interactions in the neutrino sector. Or we could have some degrees of freedom like the dilaton in string theory, which arises from the compactifications of large dimensions in models where the high energy is different. And as I said, all these issues that we are starting to see in the, for instance, in the amplitude of fluctuations at low redshift, they could all be possibly related to some different nature of dark matter, and there are many proposals in the literature. And we have now the tools, and the next generations of surveys will allow us to test these different kinds of models. And so in particular, the one that I'm interested is actually testing whether the cosmological constant is a good description of dark energy. And so one alternative, which has drawn a lot of attention in the last years, is to modify basically Einstein's general relativity. But why would we do this, since it works pretty well at large scales? So we know that actually GR is the only theory of gravity that one can write in 4 dimensions, which contains a massless spin-2 field, namely the metric G mu nu, and which is Lorentz invariant, and that gives rise to second-order equations of motion. And so this has been proven that GR is the unique theory plus some cosmological constant. So if we want to explore other modifications of gravity, we need to basically abandon these assumptions. And one could possibly, for instance, make the graviton massive, which is one avenue that one can take. We could also break Lorentz invariance, or we could add extra dimensions, additional fields, or higher order corrections in terms of covariant objects. And so one particularly interesting idea is this many type of models that have been proposed that contain basically extra dimensions. And we have models such as Kaluza-Klein theories or DGP gravity. And basically these models are very inspired by high energy physics, namely particle physics. We can, for instance, explain the hierarchy problem between the strength of gravity and the other forces. And in such theories, so the standard model is restricted to the standard model grain, and we have a 5th dimension in which gravity propagates, and this leads to an apparent acceleration of the universe at late times because of the gravity leaks in the extra dimensions. But what is interesting for our purposes today is that all these models can effectively be described as a single scalar degree of freedom, which we call phi. And so one can capture the phenomenology in terms of a scalar field phi, and regardless of the high energy behavior. So one interesting approach to this is basically to consider the Horndeski framework. This is mainly the only equation that I will show, which is complicated, but it's on purpose. So this is basically the most general Lagrangian that one can write, which contains the metric and some additional scalar field phi. And you see that the terms that are appearing in this Lagrangian are very complicated. And this framework basically encompasses many of the dark energy models that are considered in the literature. But what is interesting is that this Horndeski framework is very closely related to what we call the effective field theory of dark energy, where one just basically constructs a Lagrangian, which is consistent with the symmetries of the background. And basically we have 4 functions in the end that characterizes the deviations from general relativity. So we have the tensor speed excess, which is denoted by alpha t. It's just the difference in the propagation of gravitational waves with respect to the speed of light. We have the kineticity that basically characterizes the kinetic term of the scalar field. We have the braiding that basically tells you how much the scalar modes interact with the tensor modes in the perturbations. And then we have this generic feature of the running of the Planck mass, which is denoted by alpha m. And I will come back to this. But let me just tell you that, interestingly, despite this wide scenario of models that are available, observations coming from gravitational waves put stringent constraints on, let's say, this alpha t parameter, which characterizes the deviations of the speed of gravitational waves. And by looking at the electromagnetic counterpart, we can basically deduce that gravity waves propagate at the speed of light. And this effectively kills all these terms in the Lagrangian. And we are left only with these two terms and this one, plus the regular Einstein-Hilbert term. And so one of the surviving models is this f of r gravity, which is quite known. It's just we take the Einstein-Hilbert action, which describes gr, and we replace this Ricci scalar by some generic function of the Ricci scalar. And what this effectively does is that it gives you, again, rise to one scalar degree of freedom, which is dynamical in the system. And this is what we call the scalar arm. And interestingly, such type of theories is in perfect agreement. It's actually the one that fits better the data in terms of the inflationary potential. So you see that these are Planck constraints on the primordial tilt and the tensor to scalar ratio. And you see that this R2 inflation is actually in very good agreement with observation. This is the Starobinsky model. And so I think this is giving us some hint or that it's still interesting to consider this type of theories as alternative to dark energy. And again, just let me remind you that all of this is captured in one single degree of freedom. And so now that I've shown you more or less what we can modify and what options we have to explain cosmic acceleration, let me go and try to convince you how we can test all these alternative scenarios to distinguish them from a cosmological constant. And so we have all seen this equation. Basically, the growth of perturbations in the linear regime, so matter perturbations, is thankfully described by this simple equation, which is simply Newtonian dynamics. But effectively, what happens is that in modified theories of gravity, our function g here, which is Newton's constant, just gets replaced by some effective coupling constant, which depends on redshift and on the scales k. And so, what we can do basically is to study the evolution of matter perturbations and structure formation in the linear regime to basically put constraints on this here, the G effective that encapsulates the modifications of gravity. So what we did in this work, these are basically based in two papers. So we rephrased basically these equations in terms of this growth index gamma. So let me just briefly introduce you to the formalism. If you don't understand, it's not important. I will just give you the conclusions. And if you just understand the physics, that's enough. But basically what I do is I take that equation and I rephrase this in terms of this function f, which is basically f, it's just the logarithmic derivative with respect to the number of e-folds. So it's this quantity here. I'm sorry, I forgot to define it. But it's basically giving you information on this delta. And what this does is that it rephrases these second order differential equations in terms of delta. You rephrase that in terms of a first order nonlinear differential equation in terms of f. And so it is well known in the literature that one can approximate this function f by omega matter to the power gamma, where gamma is just the growth index. And in GR we have, and in Lambda Cdm we have this is a constant or nearly constant and nearly equal to 0.55. And so if I replace this function in this equation, I can basically rewrite this equation in terms of this growth index, and this basically becomes the dynamical variable, and we are trying to solve for this equation. So never mind about the complicated things. Let me just tell you that all this is known if we know the equation of state for dark energy, which appears here and here. And there is another unknown which appears here, which is basically the effective coupling constant normalized to Newton's constant. So there are two places where we can look for deviations here. So in Lambda Cdm, this is equal to -1, and this is equal to 1. So we know the solution in Lambda CDM, and we can explore basically the behavior of the equation of state and the coupling constant in terms of this gamma function. And this could be basically a smoking gun for the detecting departures from this Lambda CDM behavior. So what I did is I rewrote these equations in terms of a dynamical system. Basically, this is separating this equation in two vectors, basically, which do not depend explicitly on the number of evils m here. And what we can do is that we can solve these autonomous systems and look for critical points such that this condition is satisfied. And so we can plot the first phase portrait of this system. And so here I'm particularly considered the Lambda CDM case where W is equal to -1 and G is equal to 1. And so we get that we have one fixed point in the asymptotic future, which I denote A, because if it is an attractor of the system, and we have one saddle point in the past, which is S. So just so that we are on the same footing here, omega m equal 1 means we are in the asymptotic past where matter dominates. And as time goes on, we basically move in this direction. So you see that the only finite system, the only finite curve in this system corresponds to this Lambda CDM curve. And so this again is the gamma, the growth index that I introduced before. And let me just say one thing, which is crucial to our analysis, is that in Lambda CDM, this function is a monotonically decreasing function. So it never changes sign. The slope never changes sign. So what we ask is, how can we do to see, what can we do basically to see a change in the slope of gamma, and what type of theories can lead to a different sign in the slope? And so we first thought about the simplest extension is to let the equation of state for dark energy vary. We took a CPL ansatz, and we basically, once I know the functional form for W in terms of the scale factor, I can use this relationship to invert W as a function of A. And basically I can get A as a function of omega, and then inject this into this to obtain W as a function of omega. And then I can write my equation in terms of omega. So I'm rewriting my equation, not this time in terms of the scale factor, but in terms of the matter density. And so this is the equation that I'm showing here. So again, you see that the only unknowns here are the equation of state and the function of gravity. And so these are the results that I get for different values of WA. And so we basically restrict ourselves to these conditions such that matter dominates in the past. And we need to have a WA, which is positive to ensure that dark energy dominates in the future. And let me just draw your attention to the fact that in the past and most of the history of the universe, gamma is almost constant. That explains why in GR and in Lambda CDM, F to the power omega to the power 0.55 is a good description of the perturbations. But let me, if I go to, let me also say that in the past, this function depends on the equation of state in the asymptotic past. So whenever I put -infinity, it refers to the asymptotic past. And if I look to the behavior in the asymptotic future, so when omega m goes to 0, you see that in this case, there is a change in the slope, but not in the range probed by observations. So we will never be able to see this if dark energy evolves with this equation of state. But there is still a change in the slope of gamma. And again, the asymptotic value of gamma depends on the asymptotic value of W. So the next situation to consider was to consider an f of r-like bump in G effective. So in f of r theories, we know that the solution for G here is the coupling constant, basically is equal to 1 in the past, and at some point it rises up to 4/3 Newton constant, and then it starts decreasing again. And so I'm showing here in orange, I'm showing the Lambda CDM behavior, and in blue, I'm showing the solution of gamma for this function of G. So now we are interested in modifications of gravity. And you see that in this case, in the past, gamma evolves like this. And at some point, when G starts deviating from GR, we have this gamma that starts decreasing. And then again, in this situation, we have a change in the slope. So if we ever measure a gamma that has a different sign in the derivative, that means that we are outside GR. And this is why we say that gamma, the growth index, can be a smoking gun for detecting departures from GR. Again, this depends on where the location of the bump is and so on, but this is just a toy model to show that such behaviors can lead to a positive slope in contrast with what we observe in Lambda Cdm. So again, another interesting scenario which has been studied quite a lot in the literature is this DGP model, which is a fine-dimensional theory of gravity in which the Friedmann equation is modified basically to include this term, which gives rise basically to a solution that is self-accelerating. So we have an acceleration of the universe at late times without ever needing to introduce a cosmological constant. So it's kind of an explanation for dark energy. And although this model is known to have instabilities at the quantum level perturbatively, we can still use it as a toy model and study the behavior of gamma in such theories. And so you see that in such theories, the coupling constant depends on omega m. So in the past, we are at 1, but then the coupling strength of gravity starts decreasing up until we reach this point. And so the growth of perturbations is also modified in such models. And we were able to show basically where this number comes from, which was known in the literature, but to my knowledge, I never understood where it came from. And we were able to show basically that this is coming from the fact that there is a non-vanishing derivative of G at omega m equals 1. And so we have a contribution. So if I take this out, this was just the simple formula I showed before to the value of gamma. But then since the derivative at omega m is not equal to 1, then we have this thing that contributes, and we have a very different behavior from Lambda Cdm to this case. And again, let me just draw your attention that in the whole redshift range, we have a different slope with respect to Lambda Cdm case. So by studying this gamma function, we can actually test such high energy theories and say that these models are actually ruled out by observations. So I also consider in this paper the presence of an axion-like or neutrino component, which does not cluster during matter domination, but unfortunately it's a bit technical, so I will skip it. And to summarize this part, just let me tell you that beyond Lambda Cdm behaviors, some of them lead to a change in the slope of gamma, which is in contrast with Lambda Cdm predictions. And we showed the explicit origin of this anomalous value in the DGP model. And again, with the next generation of large-scale structure surveys, we might detect something if we ever measure a positive slope for gamma. So that concludes the study of perturbations in many other alternative models for dark energy. Let me consider now the case where basically we have a negative cosmological constant instead of a positive one. And this is basically motivated again by my background in theoretical physics. So in high energy physics, it's quite natural to have a negative cosmological constant instead of a positive. But the problem is that such models cannot lead to an acceleration of the universe at late times because we need a positive cosmological constant to do that. So the question we ask here is whether can we have a negative cosmological constant in the background and have some additional degree of freedom, which we call x, which depends on some function of redshift. And basically these two combinations lead to an apparent effective dark energy that leads to an accelerated expansion of the universe. And so, of course, as I said, since we observe an accelerated expansion of the universe, we can derive basically when when this will happen, and this is summarized in this figure. Basically, this is the value of the negative cosmological constant, and this is the equation of state for the other component. And you see that in all the regions, the quintessence-like regime, there is no acceleration in the past in this region, and there is some regions where we have a past acceleration, but it's only transient. And all the regions that I'm showing in white actually accelerate the universe. And these are some observational constraints coming from supernovae, but they're not important. We also consider some asymptotic solutions, so how the universe evolves in the asymptotic future. But another interesting feature in these models is the fact that basically the effective dark energy density can actually become negative. So if I consider the sum of this x component plus the cosmological constant, you see that in some regions that are shown here in magenta, sorry, the colors are not very good, but depending on the value of the cosmological constant, we can actually have regions where the energy density is negative. So most of the time when people study dark energy models, they parameterize this in terms of an equation of state W, which basically, if you have such kind of behaviors, diverges. W diverges because P over rho, when rho crosses zero, we have a W which diverges. So this will be important in the future. But let me just say that this behavior is, of course, intensified in some sense when we increase the value of the cosmological constant. And then we also studied the effect of such models that have basically on the CMB. And just to remind you that basically the shape of the CLs depend quite a lot on the content of the universe. So curvature, dark energy, baryons, and matter affect the shape of the CLs differently. And by studying Planck data, we can basically constrain the constituents of the universe. So what we did is basically we trust Planck measurements on the early universe, and this effectively constrains the matter content. And this also fixes effectively the value of the sound horizon. And we only care about the late time modifications of the universe, of the expansion rate of the universe, which of course is what we expect when we consider a constant. And once we have this value fixed and this angle, which is very precisely measured by CMB, we can basically use simple trigonometric rules to obtain a value for the moving distance to the surface of last scattering. And so we fixed this to what Planck measures, and we were able to derive basically a relationship between the Hubble rate today, the equation of state of the x component, and the omega of the cosmological constant, and this has to give you this value of the moving distance. So once we write this, we can basically obtain a relationship of the inferred value of the Hubble constant with respect to the cosmological parameters. And what is interesting about this is that actually, if I consider the case where there is no negative cosmological constant, you see that lambda CDM, so omega x equal to -1, give me 67.6, which is what we measure with CMB. But then if I start increasing the phantomness of Wx, I can go to higher values of H up to 73 for a value of Wx, which is -1.2. But then, of course, supernovae and BAO rule out these models. But when I include a cosmological constant, and namely when I increase its value, the steepness of this slope changes, and we have basically, we can reach higher values of H with less phantomness. And in the theoretical sense, this is useful because we don't want to be so far away from -1. So the fact that we have a negative cosmological constant allows us to give rise to higher values of H. And so this we can generalize in the two-dimensional plane, but it's not important. And then what we did is we wanted to test whether when we consider observations, can we say something and can we rule out a negative cosmological constant. And so what we did is we performed a nested sampling to basically compute the Bayesian evidence and compare whether the improvement in fit is worth to basically favor or disfavor these kinds of models with respect to Lambda CDM. And so let me show you some posterior distributions that we obtained. So in this case, you see I'm plotting Lambda CDM contours with respect to other two different models, one that contains a negative cosmological constant and one that doesn't. And so you see the value of H naught when I include lambda, basically, as I said, the value of H naught can be higher, but because we are including an additional parameter, the uncertainties blow up as well. And this is what we get without this kind of negative cosmological constant. And yeah, these are the posterior distributions for other parameters. But let me just show you that in some cases, this is the Bayes ratio. So giving us hints on whether this model is favored or not with respect to Lambda CDM. So if we have a value of K, which is larger than 1, we can say that the model is slightly preferred with respect to Lambda CDM. And in some cases, we have slightly more evidence than others. But yeah, most of them go up to H naught of about 69.3. And we cannot go higher than this. So even though theoretically it's possible, observation constrained this model to not go higher than 70 kilometers per megaparsec per seconds per megaparsec, basically. That's more or less for this. So just to summarize this, the models with higher evidence are found to be those with new physics appearing at large redshift. And the BAO and Supernova basically constrain the expansion rate of the universe to be close to that of Lambda CDM with an equation of state close to -1. And despite this, the negative CC remains viable. And hopefully with new observations, we can put more stringent constraints on such a presence of a cosmological constant. And yeah, although it does shift slightly the central value of the distribution, it is not enough to resolve the tension. And if the tension is actually there, we might be able from this to put constraints on such models. And yeah, that's about it. So now let me move on to some other approaches that I have been studying. So instead of considering particular models, we can also take a non-parametric approach and look for deviations from a cosmological constant. And so this is what I'm mostly interested nowadays. So this is important because we can basically falsify or rule out one of the many Lambda CDM assumptions, such as GR or the fact that the universe is flat. And also, it can point towards systematics or inconsistency between the different experiments by considering other approaches that are non-parametric and which have more flexibility to fit the data. And so let me just focus on this talk on Gaussian processes, which is quite useful for reconstruction. And one can think of Gaussian processes as a distribution over the space of functions. So basically, we have with observations, the more observations we have, the more accurate reconstructions we can have of the true function that generates the data. And so basically, when I say GP, I mean a multivariate Gaussian distribution, which is centered around the mean function, and that depends on a kernel. I'm giving 2 examples here. And basically what this is saying is instead of sampling a parametric form, we are sampling directly in the space of random functions to reconstruct the observables. And so what we want to do basically is to test whether the next generation of service can reconstruct accurately the growth and expansion history starting from very minimal assumptions. So basically the only thing that I assume is that the universe is flat and described by an FRW metric. And I also assume that the universe is matter dominated at large redshift. This is what I call Einstein de Sitter. And that the dark energy evolution is smooth and it can be approximated by a GP. So what we do is that we use forward modeling. So we basically, if a given function y of x can be accurately described by a multivariate Gaussian distribution, we can basically draw samples from this distribution. And this is what I'm showing here in this plot on the left. I'm showing if you look at the red curves, these are characterized by this parameter sigma f, which tells me how much this function deviates from the mean function. So the larger this parameter is, the larger the fluctuations around mean function, which in this case is 0. So you see, for instance, the green curve has a larger sigma f, and all the samples that I draw deviate much more. And this parameter here, LF, tells me how much the fluctuations occur as a function of x. And so you see that in the case of the green one, I have a larger value, so the curves are smoother, and the red one has a smaller value of the left, so I have much more fluctuations. And so what I do is I draw samples from this distribution, and I feed them independently to the data. What I mean by this is that I model the evolution of dark energy. So I define an effective dark energy component, and basically FDE is just the energy density as a function of redshift normalized to today's value. So at redshift equals 0, this has to be equal to 1 by definition, and it's centered around 1, which means around the cosmological constant. And I model this as a GP, and I basically when I draw samples from this distribution, I can, once I know a function FDE, I can construct my expansion rate such that I have the usual matter term plus some effective dark energy component, which basically encaptures whatever kind of behavior that it's not taking into account in the matter term. And so by doing this, I can basically, for a set of hyperparameters, sigma f and LF, get a sample of FDE. Then I can construct an H for a given value of omega m, and I can fit these expansion rates. I can calculate distances and fit them to supernovae and BAO data. And so in this figure, I'm showing the basically various samples from the posterior distributions when I fit them to a W first, or these are supernova measurements basically. And you see that those samples that retrace the true function that generates my data in dashed have a better likelihood. So this is the log of the likelihood. So all these colored functions in yellow gives me a better fit, and all this means a bad fit. And you see that all the functions that are very different from the truth have a very bad fit, and so on. And when I do this many times, I can basically marginalize over all the realization and obtain contours. But this is only from background data. Supernovae, what I can do is also that once I know my expansion history, I can solve the equation that I showed before for the perturbations. And basically, I can solve this equation and obtain the solution for F. And once I know F, this growth function that I defined before, I can construct this combination F sigma 8 in terms of basically the solutions to this differential equation. And for a given sigma 8, 0, basically I can obtain a solution for F sigma 8, and I can compare this to redshift space distortion measurements by future surveys such as DESI. And so if I include this, you see that the reconstructions are much better than before. This is because redshift space distortions are very sensitive to the nature of dark energy, as I stressed in the growth index paragraph. And so if I compare, you see that the constraints are much tighter. And again, we see that those samples retracing the similar behavior of the truth are favored by the data. And so the procedure is that I choose a fiducial cosmology. In this case, I will show a CPL model with this particular choice of cosmological parameters, but this is not important, and I will show some other cases later on. But this is just to show a worst case scenario where actually the departures are quite strong from Lambda CDM. And then I generate map data from stage 4 surveys. So I consider a Roman-like survey, which gives me uncalibrated measurements of mu, and I can translate this into background measurements of H. Then I can use DESI-like measurements to obtain basically BAO. So the transfer gives me measurements of DH over RS. RS is the sound horizon. And the radial part gives me measurements of H times RS. The problem is that we don't know H naught, nor we know RD, this quantity here. So we express all this in terms of the product, and we assume that this is fixed to the fiducial value. And then I can also generate from this fiducial model, I can generate F sigma 8 measurements by the definition. And then I can construct the combined chi-squared, and I reconstruct simultaneously for each sample of FDE. And I compare it to the observations. And let me show you the results in general relativity. So this is the fiducial model as a function of redshift. This is FDE. And again, as I said, I sample this from a multivariate Gaussian distribution, and I compare the constraints that I get from supernova only, supernova plus BAO, and supernova plus BAO plus RSD. So you see that the more I include data, the better my reconstructions. But the problem is that above some redshift of about 2, 3, I start deviating for the true cosmology. And this is understood because at some point, I don't have any more data. So at redshift 3, I already don't have much data, and the error bars are quite large. But the fact that matter dominates, if I know the value of omega m0, basically I can reconstruct the expansion rate of the universe very precisely, and the deviations are from about 2% or less. You see, in all cases. This is because, of course, this is an idealistic case where I assume that I know the matter content. So my assumption of an EDS universe in the past is justified. I will recover in the past the true behavior, regardless of the fact that I don't reconstruct the dark energy well. So this is a problem because, of course, dark energy starts to deviate from the true cosmology, but I know already the value of omega m0. This will be important in the next slides. So next step is to consider that omega m, we don't know it in reality. So we need to vary in the MCMC, but this opens up new degeneracies. And now I'm showing basically the percentage error that I get in my reconstructions. So let me first focus on the supernova plus BAO case. These are background only quantities. And so we see that at low redshift, we reconstruct very well the evolution of dark energy, but above some point, because I don't know my omega m0, basically my reconstructions start to deviate. And because also my dark energy becomes negligible at such redshifts. And so here I'm showing the expansion rates. And so you see that in this case, even though my reconstructions are not good, my H is basically consistent with within 1 sigma across the entire redshift range. And again, if I look at the reconstructions using redshift space distortion, I get a better reconstruction, but the error bars are much larger, of course. And when I consider the combination of the 3, basically I can do much better. But still, the fact that dark energy becomes negligible induces this kind of behavior where I don't reconstruct above some redshift. And this is seen also in the reconstructions of F sigma 8. So in the red curve, you see that we are consistent within 1 sigma across the entire redshift range. But the fact that my blue curve deviates here induces a deviation in the reconstructed F sigma 8. And this we can understand it because when we look at the posterior distributions, the blue contours are supernova plus BAO. You see that basically if I have a value of omega m0, which is equal to 0.3, I can basically fit as well the observations as if I have a value of 0.28, which is the fiducial value. And this is because the lack of dark energy in my fiducial model is compensated by a larger value of omega m0. So this gives me a bias in my inferred value of omega m0. And I don't see deviations from a mean function because my hyperparameter sigma f, which characterizes the deviation, is compatible with 0. But as soon as I include supernova plus BAO, you see that my reconstructions are not compatible with a sigma f0. This suggests that Lambda Cdm is not a good mean function to my Gaussian process. And in this case, I get a more accurate reconstruction of dark energy m of the value of omega m0. So let me speed up because I'm running out of time. In this case, I'm considering the most realistic case where I don't assume anything. I assume, basically, I don't assume a value for omega m0, nor I assume a value for sigma h0. And in this case, you see that, again, I see that the redshift space distortions give me much broader contours. But when I include the combination of the three, I get much more accurate reconstructions in terms of all the quantities. But again, I see that I start deviating from the truth in red, even though I still remain compatible with the observables where the data lies, basically. And so this is telling me that I can, if I assume Lambda Cdm in the past, I can induce a bias in omega m, and I cannot see from the point of observation. These are the only observables, and I can still remain in agreement and have a bias in the cosmological parameters. So what we do is that we introduce basically a new parameter in the MCMC, which we vary at each steps. We call it F99, which characterizes the contribution of dark energy at redshift 99, normalized by today's value. And what this does is basically it accounts from the non-negligible contribution of dark energy in the past. And you see that when I do this, I reconstruct the dark energy evolution much more accurately. And my contours are consistent with the fiducial value across the entire redshift range. And again, the reconstructions in terms of H and F sigma A, these times are much more accurate than with respect to the other cases. And this is coming from the fact that I removed the bias in omega m. So this I can show it in this plot. These are the distributions, the posterior distributions, when I don't consider this F99 parameter and when I consider it. So you see that what I was telling before, the fact that dark energy is not reconstructed well at large redshift induces a bias in omega m that we see here. But when I include this parameter, I basically recover the true fiducial value in all cases, also in sigma h0. And so these are the results for other fiducial cosmologies. The details are not important, but just let me tell you that these are different behaviors for FDE. And in all three cases for CPL, PDE, and TDE, basically we have accurate reconstructions of the dark, not only the dark energy density, but also the background and the F sigma A growth history when using the joint reconstructions. And so let me just briefly mention the results. This is work in progress. Now I can abandon basically the assumption of GR, and I can basically reconstruct the phenomenological function G effective. And so as I said before, this equation, the Poisson equation, gets modified to include this G effective term. And so now I consider that my background here is fixed, fixed to what I reconstruct, what I showed before. So basically, I'm using this gray line, which retraces quite good the fiducial value. I give that as an input, and now I sample this function here in what I call mu. And I'm saying that this time mu is the one that it's going to be multivariate Gaussianly distributed around 1. And so just to show you a plot, in the past, because I have good constraints on deviation from GR, I assume that I'm equal to GR, equal to 1 here. But in the low redshift regime, basically I can allow for deviations. And again, I can repeat the same things that I did before for F sigma A, for FDE, and I can constrain this function using redshift space distortions, which is the only quantity that constrains the deviation from GR. And these are the results for two toy models. So these are not inspired by any theory. I'm just considering a bump in G effective, which is shown in dash. This is the fiducial. And these are the reconstruction plus the 2 sigma. And these are the reconstructions of F sigma 8. So you see that in both cases, I can reconstruct well the true fiducial value of G effective as a function of Z. And I can get consistent measurements of sigma 8 0 without assuming any specific theory of gravity or a dark energy behavior. These are all consistent with the fiducial values. And again, I can plot the distributions. These are the values of mu at 2 redshift bins. So we see that at redshift 1.4, where DESI's measurements are most precise, I have a clear detection of a deviation from GR in a model-independent fashion, and I can recover, again, the true fiducial value of F sigma 8 in a non-biased manner. And so if I look again at the posterior distribution of sigma 8, sigma F, you see that these are not consistent with 0. So that means that GR is not a good description of the data. So hopefully in the future, when one takes this approach, one can confidently say that GR is not a good description of redshift space distortion data. I also see somewhat of a detection of the redshift of the transition when this happens. You see that in the case where I assume a Lambda Cdm background expansion history, that is the dark energy behavior is different from the fiducial one. I induce a bias in the reconstructions. So I reconstruct, these reconstructions are degraded, or in the case of the blue line, the inferred values of sigma 8 are completely biased with respect to what I expect, which is 0.81. And so this is coming from the fact that I assume a different expansion history. So this might very well be the case now when we have a biased inference of sigma 8. And so I think I run out of time. So I don't have time to discuss preliminary or ongoing work. So let me just jump straight to the conclusions and see that these are exciting times for cosmology and beyond standard model theories. We can start proving many different theoretical models with DESI, Euclid, LSST, CMBS4, and gravitational waves. I showed how the growth index characterizing the perturbations can be a valuable tool, and it's an easy tool to study. I think the negative CC remains viable, and I didn't motivate why we should consider that, but I think it's still interesting. And I think that nowadays, even more that we have reached the era of precision cosmology, we need to rely on model-independent methods to test the consistency of the experiments and get unbiased constraints on the cosmological parameters, as I showed before. And maybe this can point towards systematics or new physics. And yeah, so once we go beyond the Lambda Cdm parameterization, there is a new degeneracies that appear, and we might need a shift of paradigm if the universe is not as simple as we think it is. So yeah, that's more or less what I had to say. Thank you very much.
Really good, very nice talk. Are there any questions from the audience over Zoom or in the room? Yeah, bear in mind, if you're asking in the room, you might have to speak a bit louder so that the people in the Zoom call can, yeah. Oh, yeah, Satatri?
I thought that I was asked. Okay, so I had actually many questions in your first part, but to ask that, can you go to one of your first plots where you saw the fixed points here in LCDM? Yes, what are these blue lines here, blue arrows?
So these are basically the phase plot. These are telling me, this is my dynamical equation, my ordinary differential equation. If I start in this point in parameter space, this is my trajectory, basically. This is telling me how the perturbations evolve. And actually, if you look at the papers we discussed this, all these solutions basically corresponds to solutions where the decaying mode is non-negligible. So if the decaying mode is non-negligible, all the solutions diverge in the past, and we recover these repellers that we call here.
Okay, these are basically the manifestations of the decay.
Exactly, and this is, so the mathematical term is streamlines, if you want to know, but it tells you how you will evolve in this phase portrait.
And the second thing is that so in the next of your plot, you assume that f equal to omega m to the power gamma. Means you.
I mean, throughout this thing, when you write all the equations in terms of gamma, you are assuming that omega m to the power gamma is a good description, but this time I don't assume a constant value. I solve for gamma instead.
But the thing is that, okay, again, I think I should make also clear here, but I already discussed with you many times that for any type of screening dark energy, that should not work. That is because your omega m is not the omega m at 0, right? It's omega m as a function of z. And that becomes degenerate for any screening dark energy. And the second thing, yeah.
So you're saying if your W diverges.
Yeah, so that
this
means that
is
have the pole, the scenario is completely different.
Of course, because here this alpha is 3 times W, and so if this diverges, this is not well defined.
And the second thing is that the DGP 11 by 16, and so that is actually in literature, like people have derived that.
Yeah, but do you understand? I mean, why does it come from?
It's exactly how we got it, right? So yeah.
Oh, I never.
So basically, you saw the first term. So that your gamma minus infinity is like, so that is actually when you expand the solution in terms of.
So this.
Yeah. So if you write your left hand side is f as a function of omega n or 1 minus omega n, then that will be the first coefficient. There are the second coefficient, third coefficient, fourth coefficient. And then yes, we can discuss about it. But my point was that is actually, if I remember correctly, I think Koyama did it first. If I remember, Kazuo Koen.
I might have missed the paper, but what I like about this,
7, 8, 9.
yeah, what I like about this is that this is not only with respect to DGP, any theory of gravity which does not tend to GR in a smooth enough way will have a contribution, and you will not have basically these relationships. So naively, you would expect this coefficient, but because of this, you don't. And this is applicable to any theory of gravity that has a non-vanishing slope.
Yeah.
Omega anything.
And my last question is that in your towards your last slide, so you towards maybe so where you write somewhere this G effective as a function of K, do you really consider it as a function of K?
No, of course, no. Now I assume because at least in viable theories, the K dependence is mild, and
but I think that some of the FFR is still plagued by this.
Probably, yes, probably. I think you need to have this. So if you consider the Husa-Wiki model, you need to have this F of R0 quite large, and we have solar system constraint that kills these kind of deviations. So the dependence in K is quite mild. But this is, of course, I plan to study this in the future to see whether DESI can detect the K dependence of G effective.
Okay, I'm finished. Thank you.
Right. So can we're almost out of time. So can someone in Zoom, if they have questions, we could prioritize them. Otherwise, we can close the talk for now, and whoever has questions can remain in the room to ask a bit more. Right. Okay. I'll stop the recording now.